Hello, everybody. My name is Xinran Li, and I am a hardware engineer from FuturePlus Systems. We are a company that designs, manufactures, and markets tools for the computer design industry. Our focuses are on computer buses such as DDR memory, LPDDR memory, DisplayPort, and others. Today, I would like to introduce to you all the techniques we developed to probe and measure the bus of a DDR5 RDIMM. So I will be the only speaker for today. Thank you so much again for joining me. So before we go into the details, let me first quickly introduce what DDR5 and DDR5 RDIMM are. DDR5 stands for double data rate, fifth generation. It is the fifth generation of synchronous dynamic random access memory that computers often uses. It is quite a lot more powerful than its predecessor DDR4, and it also comes with a lot of unique features. DDR5 often comes in the form of DIMMs, dual inline memory module. It is a memory you stick into the computer motherboard. And the DIMM usually has a lot of individual DRAM chips on it that forms channels of memory. In DDR5's case, each DIMM will have two channels on it. Each channel of a memory has independent data bus connected to the memory controller of a processor. There could be what's called a rank on a DIMM that are extra DRAMs that shares the data bus of a channel of DDR5, which expands capacity of a DDR5 RDIMM or regular DIMM. So showing here is a typical looking DDR5 registered DIMM, RDIMM for short. It not only has the DRAM chips on them, these guys are the DRAM chips. Similarly here, but it also has a registering clock driver on it, RCD for short, this guy here. We'll talk more about it later on. So why is DDR5 so important, and why do we even need to test and measure it? Well, the data integrity between the processor in your computer and the memory is quite important. Even just a minor error in data storage or transmission can lead to quite significant issue, such as system crash or corrupted files or inaccurate calculations and such. This is particularly important in critical applications such as financial transactions, medical devices, data centers, or even artificial intelligence, when incorrect data can result in pretty serious consequences or failures. So it is quite important to make sure the memory bus is behaving as intended. Also, memory speed have risen rapidly in recent years, driven by demanding applications like AI that requires processing a large amount of data very quickly. However, as speed increases, maintaining data integrity becoming more and more challenging due to electrical noise, signal interference, and timing challenges. Ensuring data transfer at this speed demands advanced techniques and rigorous engineering efforts, making reliable high-speed memory design quite a significant and ongoing challenge. So as you can see on this chart here, DDR5 currently targeted at 8800 megatransfers per second is quite a lot faster than DDR4. So you can imagine lots of techniques we had for measuring DDR4 bus probably will not work due to new hardware limitation brought on by DDR5. And you can see for even future DDR5 MRDIMMs, the transfer rate are gonna get significantly higher. So we had to come up with something special, some new technique to do what we used to do. Here is a traditional way of measuring the bus of a DDR DIMM. On the left is a diagram of just a regular usage of a DIMM. You plug the green part. This would be the memory stick. This gray part would be the connector on the motherboard. You just put it in, and it connects with the memory controller and talks to the processor. So on the right is how the module level interposers we used to develop works. Instead of first putting in a DIMM, you first put in the module level interposer into the DIMM socket, and then you put the DIMM on top of it. So to the DIMM and to the memory controller, the module level interposer should behave transparently, and there will be cables on it that connects to a logic or protocol analyzer to help you understand all the information that's being transmitted on the DRAM bus. So here is a pretty good example. This is our old DDR4 DIMM interposer, FS2520. This guy here. You can see the green part here is the interposer. It first goes into a slot, then the DIMM goes on top of it, and all these blue cables are the cable that goes to a logic analyzer. Our DIMM interposers are made to be compatible with Keysight U4164A. It is the fastest logic analyzer on the market with enough inputs for DDR traffic decoding. As you can imagine, there are quite a number of signals to probe for a memory stick. So this U4164A is capable of handling an input clock of 2.5 gigahertz and capture signal up to 4 gigabits per second. So our FS2520 DDR4 interposer also supports capture up to 4,000 mega transfers per second, which is equal to 4 gigabits per second of data rate. 4,000 mega transfer per second is quite fast for DDR4. Usually DDR4 RDIMMs for server application tops out at 3,200. 4,000 is mostly for overclocked UDIMMs. But again, it is supported, and since this is a double data rate memory, the data transfer rate is twice the frequency of the clock, and the command rate, the command and address bus of DDR4 is single data rate, so it's only half as fast. Here are some iScan results we got from the Keysight Logic Analyzer software. Here, this is the clock. For the clock, we can only capture the edge of it. We cannot capture the whole signal. You can see this is a 2 gigahertz clock, and here's the chip select of the memory. And here is the address bus. This is running 2N timing mode because 4,000 again is quite fast for DDR4, but we just want to prove the the 2520 and the U4164A is capable of handling 4 gigabits of data rate. On the right here, the DQ bus, you can see it is running the full 4,000 mega transfer per second, but the eyes are fairly clear and looks pretty good in my opinion. But things are going to be quite different for DDR5. So for example here, this guy here, DDR5 UDIMM, a 6400 mega transfer UDIMM. This is actually a fairly mainstream speed you can find off the shelves. It has a 3.2 gigahertz clock, and it has a single data rate 3200 mega transfer command rate. The data rate, again, 6400 mega transfers. As you can see, the clock speed is beyond the input clock limit of the U4164A, and the data rate is also far beyond 4 gigabits per second. So there's it literally exceeding the limit of the fastest logic analyzer on the market today. So there really is no way of analyzing the DQ data bus of the DDR5 anymore. But the command rate, being single data rate at 3200 mega transfers, is still below the state mode capture limit of 4 gigabits per second. So we can still do it if we can figure out how to put the 3.2 gigahertz DDR5 clock into the logic analyzer. This is a pretty good way of doing it, because the command bus, command and address, are actually where most of the information are at. It's the most important and useful for debugging the DDR5 bus. So we came up with this clock dividing scheme. So we added a pair of clock divider on the interposer. So this clock divider chip just take an input clock signal and divide it by half and output a, for example, if we put in a 3.2 gigahertz, we'll get a 1.6 gigahertz clock out of it. 1.6 is fairly within the limit of the logic analyzer, so we can use this to sample the single data rate 3200 mega transfer command and address bus. So we only tap onto the DDR5 channel clock. The actual clock still goes straight up to the DRAMs on the DIMM. The 1.6 gigahertz channel A and channel B clock, we just pass it to the logic analyzer with all the signals we would like to probe. So here is how it looks like. This is the FuturePlus FS2611 UDIMM interposer. As you can see, there are a lot less cable coming out of it, because again, we are not able to probe the DQ, the data signals. We're only probing the command and address signals. And you can see we have some active components on it. Those are the clock dividers. It support clock frequency up to 4 gigahertz, and support a command rate of a DDR5 up to 4,000 mega transfers per second. So here are some eye diagrams we captured with our DDR5 UDIMM interposer. So with this divided clock, we need to configure the logic analyzer software to sample on 2 positions in each signal, before and after the clock edge we triggered on. This is so that the software will have all the information it needs to decode and understand the bus. This technique was able to debug DDR5 UDIMM very effectively, but the thing is, most of the important use cases with DDR5 memory, like very sensitive use cases, like what I mentioned, medical, security, financial, those cases with sensitivity for data integrity usually use DDR5 RDIMM, since they are naturally more robust with the RCD on the DIMM. So for DDR5 RDIMM, things are quite a bit different. So here is a block diagram for DDR5 RDIMM. Again, notice we have this RCD component on the center of the DIMM. Like mentioned before, it stands for registering clock driver. It takes the system clock and a double data rate DCA signal and convert them to 2 clocks for each subchannel of the RDIMM and single data rate QCA data bus and feed them into the DRAMs. So CA stands for command and address. So DCA basically is the CA bus between the memory controller and the RCD, basically between your processor and the RCD chip here. It is called DCA. And between the RCD and the DDR5 DRAMs is called the QCA. Having this RCD will reduce the load on the CA bus of the memory controller quite significantly. The DCA signal that connects between the controller and the RCD is only 7-bit wide. So instead of the 14-bit wide CA bus between the RCD and DDR5 DRAM chip, or between or even UDIM. So having less signal but at a double data rate speed will ease routing on the memory bus and enable support for more memory channel from the memory controller's perspective. So here's a more detailed block diagram of the RCD. For example, at 7200, which is the supported speed for the next generation DDR5 server platforms, the data rate and the data rate for the command and address and the data bus are both 7200 megatransfer per second, while the clock rate is 3.6 gigahertz. In this case, even we divide the clock into 1.8 gigahertz, the command and address data rate is still way too high for the logic analyzer. So we came up with a whole new way of doing it. Instead of probing the DCA bus directly, we added a separate RCD onto the interposer. So here is well, on the left, the basic topology is still the same. It's still a module level interposer. But with this RCD on the interposer, we can tap onto the DCA signal but using the interposer RCD, and we can probe the single data rate QCA bus coming out of the RCD. So thanks to the fact that QCA bus out of this RCD is only single data rate, in case of a 7200 megatransfer RDIMM, the QCA bus is going to be 3600 megatransfers, which is well within the limit of a U4164A Logic Analyzer. Here's a more detailed block diagram explaining the clock topology of our RDIMM interposer. Again, the interposer clock output is not tied to anything but the clock dividers and the logic analyzer. The host clock are passed to the straddle mount of the straddle mount connector on top of the interposer and go straight into the RDIMM being tested. It's only briefly touched by the interposer RCD and not affected by anything else. And we also need to mention that the sideband bus of the RCD and the host is separated. It's not tied to the host sideband bus. So we created a separate interface to program and power the interposer RCD. We don't tie to the host sideband bus because without special modification to the BIOS, our appearance on the sideband bus will certainly confuse the memory controller. We did put probing points on the interposer for host sideband bus probing. All of the initialization of our RDIMM interposer RCD will be handled by a separate computer running our software. The software will also put the interposer RCD in a special mode called validation pass-through mode, so that the interposer RCD will always behave transparently and will not respond to any mode register write commands from the host. It will simply just pass the D side signals to the Q side output. We did some simulations on the effect of having the separate RCD on the bus. It is an actual load on the front-end bus between RDIMM and the memory controller. On the left is the eye-opening scene at the input of the RCD on the RDIMM without having the interposer. In the middle and right is the eye-opening scene at the input of the RDIMM RCD and interposer RCD respectively. The eye size is indeed reduced by quite a significant margin on the RDIMM, unfortunately, while the interposer RCD gets a slightly larger R instead. It is an unavoidable consequence of measuring the DDR5 bus. At this point, our interposer RCD cannot yet participate in the memory training. We did some studies on balancing the eye height between the RDIMM being tested and the interposer RCD. You can find out more details in the paper, but in short, we think the current setup is the most balanced. the impact of having smaller eyes on the RDIMM RCD can mostly be offset by the memory training by the host. So here's a picture of the final fabricated assembled interposer board. You can see the output of the RCD is connected to this blue coaxial cable and that are directly soldered onto the board. The colorful rainbow cable here carries the power and I2C program interface to the interposer RCD. So now let's see some results when the RDIMM interposer is put to the test. So on the left of the slide, you can see two eye diagrams. They're measured at the input of the RDIMM RCD by the memory controller. The one on the left is what we measured when the interposer is not installed, and the one on the right is when it's installed. So we do see the similar eye drop in terms of height, like we saw in the simulations. So on the right is the eye scan we got in Logic Analyzer software. Remind you that these are the QCS and QCA outputs generated by the interposer RCD. So they have very big eye opening and the full voltage swing, but these eyes cannot represent the signal integrity of the bus. But they will provide all the information of the bus when decoded, assuming all the signals were captured correctly by the interposer RCD. So here is a screenshot on the left of the slide showing how the decoded bus traffic looks like. You can see each command and the address they're going to. And you can also see the pattern of all the commands you captured on the bottom right of the screen. So on the right is a screenshot that you can see the RDIMM being tested have passed the post-process compliance test in the Keysight Logic Analyzer software. So all these tests and information can provide extremely valuable insights to systems and component vendors to debug and validate their memory and related logic designs. So here's my contact information. Please feel free to reach out to us if you're interested in knowing more about the techniques and what we do in general. Check out my paper for more technical details about the methods and results. We're still perfecting the design of this RDIMM interposer, but the fundamental technique has been proven to work here. It is shown to be able to capture and decode the CA bus of a 7200 megatransfer per second RDIMM. We have a couple plans to improve the design lined out in the paper. Again, take a look if you're interested. Yeah, that's it. Thank you for your attention. Bye-bye.